Let's talk about electrophilic aromatic substitution, or EAS reactions. You may remember from previous lessons talking about electrophilic additions to alkenes. It's helpful to talk about those here because we go through a similar mechanism. So an electrophilic addition to an alkene, you may remember we have something like an alkene. This species is electron rich because of this double bond. We're going to add to that an electrophile, something that likes electron density, something like maybe HCl. Our alkene, this guy, is a nucleophile, meaning it's electron rich. So we're going to draw an arrow from the nucleophile to the electrophile. That proton has a positive charge, so it wants electron density. It's going to receive that electron density from the alkene. When that happens, we're going to generate a carbocation. And remember, we will put that carbocation at the most substituted position. In a second step, the nucleophile now, so this chlorine ion that has the negative charge, can come back and attack our carbocation. So now this is my nucleophilic species, and this is my electrophilic species. And overall, we call this an electrophilic addition. We have added an electrophile to our alkene. Electrophilic aromatic substitution follows a very similar path, except we're going to use benzene instead of just an alkene. In an EAS reaction, we'll start with a similar substrate, but we're going to use benzene instead. Now, benzene is a series of these alkenes that we can use. So we're going to have the same setup where benzene is going to react with some electrophile. In this case, I'll just use E+. In the first step, benzene is going to attack the electrophile and break its aromaticity to make something called the sigma complex. So here, our benzene turn into the sigma complex. Now this is a problem because benzene has lost its aromaticity. It's lost the thing that makes benzene benzene. And so at the end of the day, what we need to do is regain aromaticity here. Now in the electrophilic addition up here, we had the nucleophile come back in and attack the carbocation. This carbocation, if it gets attacked by a nucleophile, doesn't give us benzene back. So instead, all electrophilic aromatic substitution reactions will have a base that is going to take a proton from the sigma complex and reestablish aromaticity. Okay, so this is a generic example of how an electrophilic aromatic substitution reaction takes place. We are never going to work with an E molecule. We're going to be interested in what is the nature of this electrophile. One of the easiest ones to start out with is a halogen. So let's look at a specific example of an electrophilic aromatic substitution using bromine. This type of reaction is called a bromination. So the first thing that we need to discuss here is that benzene is not really good at doing this attack. Benzene likes being benzene. That's why when this positive charge forms, we take a proton and we turn back into benzene at the beginning of the day. So benzene is not a willing nucleophile, which means if I want this reaction to take place, I've really got to get that electrophile stellar. I have to get something that really wants the electron density from benzene. And so typically you'd think, well, if I'm wanting to do a bromination, I should start with bromine. But the problem is that diatomic bromine itself is not a strong enough electrophile. It doesn't need electron density enough to cause benzene to jump off this cliff. So what we're going to do is add in a catalyst first. And normally what we would use with bromine is something like FeBr3. This is an iron-based compound that can receive electron density from bromine. So the electrons are going to flow from the bromine to the iron. And what that's going to give us is a now very electrophilic species of bromine. And the reason is this bromine on the inside has a positive charge attached to it, since it is now attached to the FeBr3. Well, if I generated a positive charge here, I better have a negative charge on the iron. Now this species is electrophilic enough for benzene to do its attack. So now we'll have benzene come into the picture. The electrons are going to flow from benzene to the bromine and break onto the bromine. Notice I attacked that outside bromine instead of this inside bromine. We need the electron density to go somewhere, so it's obvious that it should go to the positively charged bromine here. A lot of students want to attack that initially, and you can't get the electrons to work out. We have to push something off, so it's going to attack this outside bromine first. Once it does that, we're off to the races. So this is that first step where benzene attacked the electrophile. This is benzene attacking the electrophile. That's going to make our sigma complex. That's not a great benzene. It's all right. Where we've added a bromine to the benzene structure. And now that second step is we need to reestablish aromaticity. So we have a base come in to take the proton from the sigma complex. And this base can be a lot of things. It can be the FeBr4 minus, it can be water. A lot of different things can take this proton. The base will then come remove the proton, which will then reestablish that double bond and give us a brominated benzene.